Now that we've developed all these mathematical tools for quantifying the properties of mixtures, we're now going to apply those tools to different sorts of systems. Um, for this chapter, one of the systems that we're going to emphasize is a case where we're looking at vapor-liquid equilibrium. And for chemical engineers, this is a particularly important case because your separations course is going to focus very heavily on vapor-liquid equilibrium. And so in this thermo class, I'm going to give you an introduction in how you analyze vapor-liquid equilibrium. And specifically, we're going to start with looking at the case where the total pressure in the system is very low. And so for liquid equilibrium, the sort of model system I want you to consider is once again a piston cylinder system where underneath the piston you have a mixture in which the mixture is both in the liquid phase and in the vapor phase as well. And so in each of the phases you have two different species, species 1 and species 2. And so species 1 and 2 are both in the liquid phase and also in the vapor phase as well. If you want a more concrete example, you could think of species 1 as being acetone and species 2 as being methanol, because unlike when we talked about Henry's law, where the gas is only sparingly soluble in the liquid, if we're dealing with acetone and methanol, both of these things are miscible with one another over the entire composition range. Okay? All right, and so this is the basic sort of idea that you should have when we're talking about vapor-liquid equilibrium. Just think of a piston cylinder where all of our stuff is underneath the piston, and our system can be both in the liquid and vapor phases. And generally, I'm using x's for the liquid mole fractions and y's for the vapor mole fractions. And generally, these mole fractions are not equal to one another for a given species, except for in a very special case when we form azeotropes. And we'll talk about that specifically later on. Okay? In any case, to analyze this sort of system, we're going to make a couple of assumptions. And so, for the vapor phase, to make our lives a little bit easier, we're just going to treat the vapor phase as an ideal gas mixture. And for the liquid phase, we're going to kind of treat the liquids as being incompressible. Or in other words, the chemical potentials of the liquid phase are not a function of pressure. And this is a fine assumption if you're dealing with low pressures relative to the vapor pressures of each of the species. Okay, so that's why, once again, I'm saying we're only looking at the low pressure analysis. Okay? All right. And so those are our two assumptions. And so in order for the vapor and the liquid phase to coexist at the same time, in order for that to happen, the criterion for that is that at equilibrium, the chemical potential of the vapor phase has to be equal to the chemical potential of the liquid phase for each of the species. Okay? And I'll call this equation 1. And I want to clarify that for this equilibrium criteria, I'm saying that the chemical potential for species I in the vapor phase is equal to the chemical potential of species I in the liquid phase. What I'm not saying, is that the chemical potential of species 1 in the liquid phase, I'm not saying that it's equal to the chemical potential of species 2 in the liquid phase. In fact, I'm going to write here that generally the chemical potential of species 1 in the liquid phase is not equal to the chemical potential of species 2 in the liquid phase. And and the same with the vapor phase. Okay, so make sure not to confuse those things together. This is true, but these are typically not true. Okay? All right. And so when we think about the chemical potential in the vapor phase, we could say that that's equal to the molar Gibbs energy of the pure component in the vapor phase at some temperature and pressure plus RT ln of the partial pressure, which is Yi times total pressure, over some reference pressure. Okay? And then the same, or for the liquid phase, we could write it like this. Where for the liquid phase, we're going to write it in terms of activities. I'll emphasize that these terms are for the pure component. Okay. All right. And so at equilibrium, for equilibrium, the system has to be in thermal, mechanical, and chemical equilibrium. And so thermal equilibrium, all the pressures or all the temperatures are the same. For mechanical equilibrium, all the pressures in the system have to be the same, and specifically that would correspond to the saturation pressure or the vapor pressure of a particular species. And so Pi is equal to P sat I. Okay? All right. And then for the pure component molar Gibbs, those have to be equal to one another as well for the vapor and the liquid. Okay? And so those are the equilibrium criteria. And then what I'll do is for our reference pressure, I'm going to set it equal to the saturation pressure for species I. Okay? All right, and so if I apply all those things, so if we go back to equation 1, we know that the chemical potentials of both the vapor and the liquid phase for a species are equal to one another. So we have Gi V T P sat I plus RT ln Yi P over P sat I is equal to Gi L T P sat I plus RT ln of AI. Okay? At equilibrium, these things are equal to one another. And so this and this are equal to one another. So if they're equal and they're on both sides of the equation, we could cancel them out. The RTs are on both sides of the equation. We could also cancel those out as well. We can now rearrange this equation. And what we get is that we have Yi P over P sat I is equal to the activity. And based on how we defined activity in the previous videos, we could say our activity is equal to the mole fraction of species I in the liquid phase times its activity coefficient and this Yi times total pressure, once again, that's just the partial pressure. So if we rearrange this equation, what we get is that the partial pressure of species I in the vapor phase is just equal to the mole fraction of species I in the liquid phase times its activity coefficient times its saturation pressure. Okay. And so this equation may look familiar, though we're going to have to make one more assumption in order to get it to the most familiar form. In any case, this is a very useful equation because it relates the partial pressure of the species in the vapor phase to its composition in the liquid phase. Okay? In order to use this equation, what you need are the vapor pressures of the pure compounds, and you also need some way to calculate the activity coefficient of the liquid mixture. Okay. Now, if we're dealing with an ideal solution, for an ideal solution, the partial molar Gibbs excess, by definition, would be equal to 0. And so if that's equal to 0, and our activity coefficient is the exponential of G excess divided by RT, if this is equal to 0, we get exponential of 0, which is just equal to 1. And so if gamma I is equal to 1, our equation then just becomes Pi is equal to Xi P sat I. And this is what you saw back in MEB1. This is known as Raoult's law.